All right, here we are with section 2.3, limits. Formally, we're going to start looking at these limits more closely from an algebraic, non-numerical perspectives. And we're going to start off by practicing and being introduced to our basic limit laws. So theorem 1 here is the collection of all of these basic limit laws. And this is a lot to parse for sure, but I'm going to encourage you to just think of these rules, these laws, as telling you what you already want to do is okay to do. So what do I mean by that? Well, this is really just saying limits work the way that you would hope them to work. If you want to take the limit of two things added together, well, it's the same thing as just taking the limit of each piece and then adding the answers together. That's great. Same thing for subtraction. If you have a constant times your function, so if you have like 3x or 5 times the sine of x, so you've got some real number k times a function. Well, since the real number doesn't depend on x, it's a constant, the limit only potentially affects, the function f of x. So that means you can just take the limit of f and then multiply the answer by k. Okay, and now we have products. If you want to take the limit of two things multiplied together, just take the limit of each piece and then multiply the answers. Similarly for quotients, if you want to take the limit of two things being divided by one another, you can take the limit of each piece, the quotient and the divisor, and divide those limits. And that's your answer. Now there's one little caveat here, and that is you have to make sure that for the function in the denominator, if the limit of that term is 0, then this doesn't work. But really, it's so ingrained in your head that you shouldn't divide by 0 that should also be pretty clear. Okay? 6. If you take the limit of x to the n, where n is any real number, then you can just plug in c to the n. There's one little thing here that I do want to add that's important here. Let's go ahead and just say that provided c to the n, well, how do I want to phrase this? Let's phrase it in the way that, so here's the issue I'm thinking of right here. If c is 0 and n is negative, what's that look like then? If n is negative, that means we have something like, for example, let's say -2. Then this really is the same as (1 over x squared). So then if c is 0, then we get division by 0, which doesn't work. So how about we correct this, make it a little bit neater, and just say real numbers, and I'll put a subscript on this and say only the non-negative real numbers. That's better. And I'll have to do something similarly for here. Okay. So this one says the limit as x goes to c of f of x, all that raised to the nth power, then you can just pass the limit inside, do the limit of the inside, and then raise your answer to that power. And really 8 is the same thing as 7. It's just a more specific notational thing, because remember that an nth root of something is just raising to the 1 over nth power. So really, these two things are the same. In other words, limit of a root of something, you can take the root of the limit of that something. Again, what we're going to do here is just apply these in examples, and they will become second nature to you. Okay? Big thing that we do have to mention before we move on, and that is all of these limit laws, they are predicated on the assumption that both the limit of f and g exist independently of one another. Because it is true that you could do something rather strange. You could have two functions, and maybe their limits don't exist. But when you add, subtract, multiply, divide them in such a way, the collective limit then exists. Arithmetic with division by zero and infinities, things like that, can get a little bit hairy. So it's really important that if you're going to use these limit laws to split things up, that your limits exist independently of one another. If they don't, you could run into some weird issues.